In 3, 2, 1. I think I heard a sonic boom. I think we broke the sound barrier. 767 miles per hour is the speed of sound through air, and accelerating a projectile to this speed using a purely mechanical launcher like a trebuchet has been a dream of mine for several years now. At its core, a trebuchet is just a seesaw. A weight falls due to gravity, which whips a projectile round in a sling to release it at high speed. But there's a physical speed limit built into a traditional trebuchet design, and it's gravity itself. As a weight falls towards Earth, it can't accelerate faster than 9.81 meters per second squared. So if I drop this weight from about 2 meters high, it hits the ground at just 6.2 meters per second, less than 2% the speed of sound, and dropping a heavier weight won't make it fall any faster. An alternative way to avoid this gravity limitation is to use large rubber bands, as they can produce huge amounts of force with very little mass, and can therefore accelerate a lot faster. And an elastic-powered supersonic trebuchet was built a few years ago.
1.
Now this thing is absolutely insane, but I've always wanted to build one that drops a weight. So let's build the world's first gravity-powered supersonic trebuchet. Now for reasons already mentioned, this won't be a traditional trebuchet design, but we can use some other physics methods to convert the force of gravity into much higher speeds. You see, a traditional trebuchet lever design is a bit like driving a car in first gear. There's lots of torque for launching large projectiles, but the weight quickly reaches the bottom of its swing, a bit like hitting the engine rev limiter. Whereas this design will remove the direct coupling between the weight and the main arm, so the weight will have a bit more mechanical advantage, a bit like shifting up the gears for more speed. So the weight will slide down this tall portion of the frame, and then on the other half of the frame we can mount the axle that the main arm will be attached to. Then we can link the weight to the main arm using a rope to create a ratio to convert the slow moving large force of the weight into slightly less force but much higher speed at the arm. To achieve this ratio, the weight will be suspended by a 3-to-1 pulley system, meaning I can lift the weight with only a third of the force on this rope. But it also means that this rope will travel 3 times faster than the weight when it falls. And we can use this rope to spin up the arm to very high speed. But this also requires energy, and just like a flywheel, a heavier arm will require more energy to move. To avoid this, I've been testing a prototype arm that's relatively short, and a sling that's double the length of the arm, which is quite unusual for a trebuchet. But it works by wrapping the sling around this curved section, keeping the projectile close to the main axle. Then as the arm spins, the projectile unwraps around the curve, narrowly misses the ground, and whips out to its full radius right at the perfect angle. And this design keeps the tip speed of the arm relatively low compared to the speed of the projectile, meaning it doesn't need to travel anywhere near the sound barrier, which should help minimise aerodynamic drag. But the arm must be very strong to survive the huge forces of the projectile swinging around at supersonic speeds. And it also needs to be lightweight to reduce the amount of energy required to spin it. So I'm going to make the arm out of carbon fibre, which I can cut on my CNC mill. I initially designed this A-frame style arm and ran it through some stress simulations to see how lightweight I could make it. But before committing to the expensive carbon fibre, I 3D printed a test piece to validate the maths, and immediately found a problem. Because the tension in the sling will apply a backwards force on the arm, the front edge of the arm is in tension, which it handles perfectly, but the back edge is in compression, which is causing the arm to buckle. Now 3D printed plastic is obviously far less rigid than carbon fibre, but at the speeds we're aiming for, we can't take any chances. To fix this without adding any extra weight, I removed material from the front edge of the arm and beefed up the rear, and this new asymmetrical design held slightly more force. I then added a second cross brace to try reduce the buckling further, and it held even more force. I then tried a few other designs with diagonal braces and single thick struts, but the double brace design was the undeniable winner. So let's make the arm. Now cutting carbon fibre is very dangerous, specifically the dust is incredibly hazardous to breathe. So I rigged up a custom HEPA filter to my vacuum and wore a suitable dust mask. I also constantly sprayed it with water to trap the particles before they became airborne. Once finished, the resulting black sludge was a bit of a pain to clean up, but it proved how well the water captured the dust. And now we have a perfectly rigid carbon fibre arm weighing just 116 grams. But carbon fibre is terrible for holding precise bearings or threads, so I machined a custom aluminium hub which the main arm and counter arm can bolt directly onto, creating a strong yet lightweight assembly and should be balanced for reducing vibrations. Now these parts took me a while to manufacture myself and also required me to build my own CNC milling machine. But if you need some parts manufactured, then I highly recommend checking out PCBWay, who offers CNC machining, sheet metal fabrication, 3D printing and injection moulding. Simply upload a CAD model of your part and get an instant quote. In fact, for that price and lead time, I would have been better off getting PCBWay to make this part. And there's a wide range of materials to choose from, which my CNC isn't even capable of machining. So, if you need some parts manufactured for an upcoming project, check out PCBWay at the link in the description below. To spin up the arm using the rope from the pulley system, we need a drum that the rope can wrap around. And thanks to 3D printing, we have the ability to design a custom drum profile to optimize the torque output during launch. So I designed this tapered drum that starts at a large diameter for lots of initial torque, and then reduces down to a smaller diameter for more speed, a bit like shifting up the gears on a bike. And this attaches to the arm with 6 large bolts to add additional strength to the 3D print, and the whole assembly can slide onto the main axle. For the drive rope, I've chosen to use ultra high molecular weight polyethylene, often referred to as Dyneema, which at just 4mm thick is rated to 1.5 tons of tension, so it should be able to handle the forces of this trebuchet with minimal stretch. So we now have a lightweight arm that can be accelerated using a falling weight, but because of the 3-to-1 pulley system, it takes 15 rotations to get up to speed. So we need a precise method of releasing the projectile at about 2000 RPM. And at this speed, the release window is only about 2.5 milliseconds wide. I thought about maybe using the falling weight to hit a trigger at the bottom of its fall, but then this trigger has to somehow attach to a spinning release on the hub. And I didn't want to go with an electronic release as I want to keep this trebuchet purely mechanical. But then I realised the unwinding of the drive rope is essentially a built-in countdown timer. So I designed a hinged flap directly into the drum, which sits over the rope once it's wound up. Then to link this hinge to the projectile release, there is an internal channel through the drum to pass through some string. And the string connects the hinge trigger to a spring-loaded ball catch on the side of the hub. So as the arm spins up, the projectile is locked securely in place. But the split second the rope finishes unwinding, the hinge is opened and the projectile is released. Initially, I'd planned to use a 10mm ball bearing as the projectile, but a supersonic steel ball bearing is essentially a bullet. So to keep things slightly safer, I'm going to 3D print the balls instead. This lets me perfectly tune the weight and diameter, and the lower density means they'll lose energy much faster in the air, and not travel quite as far. But the projectile isn't the only thing that will be going supersonic. The sling also has to travel with it, which at such high speeds, aerodynamic drag could be a huge issue. So I found some much thinner 1mm diameter Dyneema rope, and amazingly this stuff is still rated to 130 kilos. Then to build the sling pouch, I spliced 2 lengths of rope into a loop for the main structure that will wrap around the ball, and I then used some thinner rope to create a zigzag pattern to cup the projectile, as it's essential that the ball doesn't fall out during launch, because then it might fire backwards, which wouldn't be ideal. The final sling release at the end of the arm is just like any other trebuchet. One end is permanently fixed to the arm, and one loops over a smooth pin. So as the projectile swings round in the sling, the loop slides off the pin and the sling opens, releasing the projectile. Right, so today is initial testing day. Just test all the release mechanisms. So if I wind it up twice just to get the latch in position, then attach the release rope, we should be able to attach the sling. So the sling wraps around the other end,
And the ball clips in position just like that. Okay, it is locked and loaded. Here we go, you ready? In 3, 2, 1. Oh my god! Oh my god! Oh, we found part of it. It's a bit lopsided. So it bounced off one of the trunks. Nice.
Seeing this thing launch for the first time was incredible. The 10 kilogram weight accelerated the arm up to 1100 RPM in 1.3 seconds and released the projectile at 328 miles per hour, which is a new personal record. But there's a problem. With the weight raised to its full height, the machine holds 192 joules of gravitational potential energy. And as the weight falls, this potential energy is converted into kinetic energy as both the weight and arm gain speed. Then just as the projectile is released from the hub, the weight only has 22 joules of potential energy left and has gained 10 joules of kinetic energy. So most of the energy has been transferred to the arm, which is exactly what we need. However, the total energy remaining in the trebuchet is just 110 joules, meaning it's lost nearly 43% of the initial potential energy just during the spin up of the arm. Then as the projectile whips around in the sling, it's released with a kinetic energy of 65 joules, giving an overall efficiency of just 34%. Now the reason this is a problem is because I designed all the components in this trebuchet to withstand a 40 kilogram weight, and with the current drop height and projectile size, that would mean an efficiency of about 50%. And as we ramp up the speed, the efficiency is only going to reduce. As most of the energy seems to be lost during the spin up of the arm, I want to make it more aerodynamic. So I've 3D printed a sharp leading edge to help the arm slice through the air. And I also wrapped the whole thing in model aircraft laminating film to cover the gaps. And if we do a side-by-side spin test using just the weight of the pulley, they seem to spin at similar rates. But after 6 rotations, the drag on the old arm starts holding it back. And by the end of the drop, the new aerodynamic arm is a full rotation ahead, giving us a 12% increase in RPM. I then thought I should take this further, and as the tip of the arm is spinning the fastest, I swapped out the bulky sling attachment for a new aerodynamic version. And I also realised the sling guide on the opposite end of the arm might be acting like an air scoop, trapping high pressure air, so I printed a new one with vents to let the air escape. And the results were quite surprising. This new setup finished a full 1.5 rotations ahead of the original arm, with a 17.8% increase in RPM. And that's only at low speeds. At the full power speeds, aerodynamic drag scales exponentially, so the difference will be huge. I also remembered that every gram at the tip of the arm will also reduce the RPM, as it requires extra energy to accelerate. So I redesigned the sling mount to be 100% 3D printed, removing most of the metal hardware and reducing the weight by 40%. But I wasn't sure the 3D printed sling mount could survive the huge forces during a supersonic launch, so it needs testing. Now, my digital force gauge maxes out at 500 newtons, but the sling tension during launch could be up to 800 newtons. So to test it safely, I used the mechanical advantage of the 3-to-1 pulley system built into the trebuchet itself. So for every newton on the scale, the 3D print experiences 3 newtons, and with enough tension to simulate a supersonic launch, it held up fine. So with all the new aerodynamic arm modifications, there's just one more thing to optimise. The original transmission drum was leaving energy on the table, as it only raised the weight 1.7 metres, which doesn't make full use of the frame. So I redesigned the drum with a new taper profile, which now has more wraps at the larger diameter to give more initial torque, and a 20% smaller final diameter to hopefully increase the final speed. And now when I wind up the drum, it lifts the weight to a full 1.9 metres, storing an extra 12% of gravitational potential energy, which means we now only need an efficiency of about 46% to go supersonic. I also bought some biodegradable filament to 3D print some new projectiles, as the chances of finding a 20mm ball after launching at such high speed will be almost impossible, so these balls should biodegrade within a few weeks. But with all these modifications, can we even break the sound barrier?
Well, today we're going to hopefully find out. So I've set up the trebuchet to aim directly into that field. There's about 5 kilometres or 3 miles of nothing but fields, even past that row of trees over there. So we should be safe to break the sound barrier, if we can do it. Right, here we go. First test launch with 10 kilos. In 3, 2, 1. Wow, that never gets old.
With the same 10kg weight as the earlier test, the new aerodynamic arm reached 1,248 RPM and launched the projectile at 394 miles per hour, 20% faster than before and with an overall efficiency of 43.7%. A bit short of the ideal 46%, but let's see how it does with more weight.
So it's now time to increase the weight from 10 kilos to 20 kilos. In 3, 2, 1. Nothing's broken. It's time to ramp it up to 30 kilos. In 3, 2, 1. So now it's time to do the test with 40 kilos, which, according to my calculations, should go supersonic. There's only one way to find out. 40 kilo test. In 3, 2, 1. I don't think that did it, did it?
Unfortunately, no it didn't, but it wasn't far off. The 40kg weight accelerated the arm up to 2,336 RPM and released the projectile at 716 miles per hour, just 51 miles per hour short of the sound barrier, with an overall efficiency of 39%. But with the slightly late release of the sling, it's cool to see the ball strike the ground in a cloud of dust.
So nothing's broken. It's still launched successfully, went down a little bit. Seems like as we increase the weight, the release angle goes down, so I've advanced it slightly up there. I'm going to try 50 kilos because that didn't create a sonic boom. The only problem is it was never designed for this much weight, and also I can't fit the clips on the weights, so I've just got to hope they don't fall off. 50 kilos, is this a bit too far? Never. Right, here we go, 50 kilos. Break or boom. Sonic boom, hopefully. In 3, 2, 1. I think something broke. Oh, the sling snapped.
As expected, 50 kilograms was just over the design threshold for this trebuchet, which shows how tight of a margin we're working with. And also looking back at the 40 kilogram test, the arm was pretty close to its limit too. So in order to reduce the loads on the trebuchet and also the kinetic energy required to reach the sound barrier, I'm going to reduce the mass of the projectile from 6 grams down to 4 grams, which also has a smaller diameter for less drag. Also, after the 50 kilogram test, the hub latch had broken because when the sling snapped, all the energy from the weight was transferred into the hub, which wrapped around the latch and broke it off. So I've printed yet another new drum with a different groove profile that actually increases in diameter on the last rotation, because I noticed from the slow motion footage that the projectile's fastest speed was at this point in the rotation. So the final increase in diameter should give a last little boost of torque. And this new drum also has a new release mechanism, which is simply a loop of string hooked over the drive rope and attached to a pin, which doesn't allow for any adjustability of the release point, but should be more reliable, and won't break if it gets wrapped up in the drive rope after launch. So let's head out for another test.
This has to be it. Come on. Okay, here we go. Hopefully Supersonic Trebuchet. In 3, 2, 1. I think I heard a sonic boom. I think we broke the sound barrier. I heard an echo over there and over there. Nothing's broken. I think we just broke the sound barrier.
As the weight falls, it accelerates the arm up to 2,342 RPM, with a tip speed of 274 miles per hour. And as the projectile leaves the sling, it travels 1.94 meters in just 5.6 milliseconds, giving a final speed of 346.4 meters per second, or 776 miles per hour. Just 9 miles per hour over the sound barrier. I started doing the calculations for this project almost 6 years ago, and have been building trebuchets since the age of 12.
3, 2, 1.
But I never thought I could actually build one that would go supersonic. However, with the accessibility to modern engineering tools like computer-aided design software, a homemade CNC milling machine that can cut metals and carbon fibre, and the endless possibilities of 3D printing, the Supersonic Trebuchet has now become a reality. Thank you very much for watching.